see fit. Hello, this is Carl from LunchboxSessions.com. Thanks if you've been with us through the entire series this spring and summer. This is our number 6 out of our 6th out of 8 in the series. There's one more to go in July 14th, and then one more in August. And if you're new, joining us for the first time, then thanks for tuning in this morning as well. That's great that you've joined us. It may not be morning where you are, and just thanks for giving us your time today. I see so far we've got people joining us from Kuwait. Wow, that's far away. Great. Welcome to you. Way over in India. That's about as far away as I can travel before I start coming home the other way. So that's terrific. And I think we've got some friends in here from Ontario. A shout out to the team at Higginson Equipment. Welcome joining us this morning. That's great. Let's have some fun today, learning a little bit about hydraulic servo valves, perhaps a little bit about their function, a little bit about applications, and a wee bit about the troubleshooting that goes with them as well. Hydraulic servo valves is such a fun area to work with because now you're into the really precise aspects of motion control. It really is that part of hydraulics that turns it into robotics, if you will. And just so many great applications. When you think of flight simulators, that's probably the really fun part. And then just so many other very precise industrial applications. So I've got a whole assortment of servo valves on the table here this morning. Some, unfortunately, are cut up and they're in tiny pieces now, but that'll help us get inside a little bit. We've got some exciting 3D sequences to show you as well. Some of those are brand new, so stay tuned to see some of that. And just like we were running a moment ago, we'll have the hydraulics fired up once again and see some things taking place in live motion. And on that note, be very careful around hydraulic systems. Our short 1 hour today is not enough time to impart all of the skills needed to work safely with hydraulics, especially if you have to do some repair or diagnostic work. So make sure you receive the necessary training in that and receive mentoring from someone who's done that kind of troubleshooting before. It's automation that we're working with, so keep in mind that whenever there's sensors involved, it could be very easy to trip a system into action and automatic motions could take place. Be aware of those hazards. You may need to log into your Google account or your YouTube account to join us with the live chat, and we really welcome you to do that. We'd love to hear from you. We'd love to answer your questions if they pertain to today's topic, servo hydraulics, and feel free to jump in on that. If you've got some questions for us that are not necessarily tied directly to our topic today, then feel free to fire those in on email. You can use info@lunchboxsessions.com, or if you want to converse with me personally, I'm pretty easy to find on LinkedIn. I spend a lot of time there, so look for Carl Dyke, Industrial Teacher, and you should be able to find me in a hurry, and perhaps we can chat that way as well. A shout out to my friends at fluidpowerworld.com. Fluid Power World's a great resource on components in the world of hydraulics and pneumatics. Great place to learn about system engineering, great place to learn about design. And keep an eye on that website because this year the Fluid Power Technology Conference goes online. And it starts right away now in July. Tuesday, July 7th, coming right up. And the first speaker, the first session will be Joe Kovac. You won't want to miss that. Joe's got some very innovative thinking about the future of hydraulics. I heard him speak last November in Cleveland. You won't want to miss that one. All the details on fluidpowerworld.com, so find that information there. Today we have two sponsors, and the first one, Delta Computer Systems. For nearly 40 years, Delta Computer Systems has supplied motion controllers and other industrial products that enable better performing machines. Delta's RMC motion controllers are used for hydraulic, pneumatic, and electrical closed-loop control in a wide array of single and multi-axis control and testing applications. Delta's high-performance motion control product line includes the RM75, RMC75 2-axis, the RMC 158 axis, and the RMC 200 32-axis controllers, and provide built-in support for precise closed-loop position, velocity, pressure, and force control for a broad range of industrial applications. The motion controllers are provided with a powerful free software suite called RMC Tools, which includes automated wizards for programming, tuning, and plotting of motion results. For more information, visit deltamotion.com. Also sponsoring today is Servo Kinetics, with servo and proportional valve servicing for Eaton Vickers, Parker, Moog, Pegasus, Bosch Rexroth, Star, Yukon, and many more models. The lab at Servo Kinetics uniquely features custom drive electronics with versatile settings that precisely simulate the OEM specifications and that also match the client's final application and installation. There is never a doubt that your valve will leave the Servo Kinetics lab ready to be put right back into service. With over 45 years of experience serving nuclear energy, wind energy, aerospace, and all industries with closed-loop servo and proportional valve automation, you simply cannot find a more qualified firm than Servo Kinetics for your next servo or proportional valve repair or recalibration. For more information, visit servokinetics.com. All right, that word servo, what does that mean? Or maybe the word servo mechanism. That will be our pop quiz question of the day, and we'll answer that one a little later. Maybe you hear that term from time to time and haven't stopped to think about exactly what it means or what the root of that word is. So the definition or the larger meaning of the word servo or servo mechanism, that'll be our pop quiz question. Well, let's have a look at servo hydraulic valves in their native environment. We usually start off with some photographs from our travels through industry. I'm just going to move my mouse over here. There we go. And I'm starting off with the images that show the best lighting. When we take pictures in the plants and mills that we visit in our work, quite often the lighting is poor, and a few photos have just turned out so terrifically. So I'll start off with those. Oh yeah, very typical application here with a tie rod cylinder, and is so often the case. The servo valve itself is mounted right on the cap end of the cylinder, and so that makes it very easy to find the connection port to the cap end or the blind end of the piston. And you see a solid steel rod, or sorry, a solid steel tube running up to the rod end port. And so perhaps there's a good reason why that servo valve gets mounted right on the cylinder. And maybe more about that as we move along. And then, is so often the case, sticking out the back end of that cylinder is the electronic controls that go with a transducer that is following the exact position of the piston and rod on the inside. We'll have a look at those. Here's another style of valve. This one has a rotary style function for driving the position of the spool inside, but again, it's mounted right on the valve. This one is a vertical orientation, but otherwise a fairly similar or typical application for servo hydraulics. You can't see the displacement transducer for the cylinder quite so easily. It's kind of hidden behind that hydraulic hose on the left, but you do see the electrical connection cable there for it. Yeah, another typical installation here with a Moog valve on top. That's a two-stage valve, and we're going to get into that one. Hey, we might even take that. Do you see that small, well, that's a fairly large screw actually, that slotted screw above the connector there? We're going to remove that out of the valve that we've got here and see what we can learn in there. Hydraulic oil does not come out of that port. It shouldn't when you remove that screw unless something went terribly, terribly wrong. What about this extra cylindrical piece just off to the side? Perhaps you recognize that. Servo valves require an awful lot of highly filtered, really clean fluid. And so often the case is to see a full pressure filter right at the servo valve. And hey, I'm assuming that Mark has joined us this morning. I haven't looked at the list there, but Mark will be there with a wrench beside his name, and will be joining in to try and answer some questions. And Mark may have some things as well to share about the cleanliness requirement for the fluid. If you joined us on our last live session a few weeks ago, exactly 2 weeks ago, we talked a lot about keeping the fluid very clean and free of particle contaminants. And when it comes to servos, that demand is at its highest. Right, the displacement transducer on this particular installation covered with a steel cap. Great way to keep that sensitive electronics from receiving damage from something that might bang into that assembly. But here it is a little bit more exposed once again. You can see the displacement transducer out the back of the cylinder. The valve is mounted directly on the cylinder, and keeping that valve directly mounted at the cylinder creates what is often referred to as a very stiff servo loop, meaning that there really isn't any spongy or expandable elements between where the valve is and where the cylinder is expected to move. Perhaps only a little bit of compressibility left in the hydraulic oil, but certainly no hydraulic hoses or anything else that could flex, bend, or stretch. And in so doing, helps keep that servo control loop that we're going to talk about very stiff and very accurate. Is it mandatory that you keep the valve mounted directly on the cylinder? Absolutely not. If the response time for the cylinder to move to position is not terribly critical, and perhaps the final position not as critical, it may not be necessary to have the valve directly on the cylinder. You'll see some installations like that here in a moment. Another fairly typical installation, this time with the filter close by. Valve mounted in a horizontal orientation, not an issue. Yeah, a number of very typical factory or mill installations for a servo valve on a hydraulic cylinder that may be just generically referred to in the plant as a hydraulic servo axis. Here's the first time we're seeing a direct drive valve, a linear direct drive valve. That earlier one that was cylindrical in shape, the second photo, that was a rotary direct drive valve that we'll have a look at. This one is a linear direct drive valve, and that's becoming very, very popular too, where the solenoid, in some cases, manufacturers like Parker referring to their coil works as a voice coil, similar to what you would have in driving the magnet and cone of a speaker, and a number of manufacturers producing valves where the solenoid element is directly driving the spool and that there isn't a pilot stage. And that is what you're seeing in this particular instance. And then some of you may say, well, isn't that just a proportional valve? And then maybe we'll end up in a little bit of a discussion of, is there a big difference between what is called a proportional valve and what is a servo valve? And maybe a servo valve is just a particular and accurate type of proportioning valve. Let's move along. I think this is our first instance here of valve off the cylinder. The cylinder is down below. You can see the displacement transducer down low, and there isn't any room in that particular area of the machine for the valve to be mounted directly on cylinder. So that valve is mounted above, and this is a three-stage servo valve. We'll see some more examples of that as well, where the flow requirements are quite high and a very large third stage spool is necessary to deliver the required flow. That's our first example of valve mounted away from the cylinder. Here's another. Here's a number of cylinders in a row, and if I remember right, I believe these servos are moving feed rolls into position. You can see the displacement transducers covered by a steel cap, and the valves are the direct drive type, and they're just close by, perhaps only a short length of hydraulic hose between each cylinder and each servo valve. And perhaps you sacrifice a little tiny bit of accuracy, but there's other conveniences as well with the valve not necessarily mounted on the cylinder. What's left in my slideshow here? Yeah, a fairly typical installation in this case. And again, we see that that screw in the cap of the Moog valve that can be removed, and we'll do a little bit of mechanical nulling together. We're going to put a 1/8 hex key into that hole and see what happens. And one more example of servo valve. The servo valve is located on the cylinder, very large cylinder, but here is another example of a 3-stage. So we've got a torque motor, an output spool, and then a final 3rd stage output spool for a very large amount of flow going to a very large hydraulic cylinder. And we see the MDT perhaps covered in a bit of dust, but there it is down below. So just some very typical installations, and perhaps we'll end with this one just for a moment of what maybe is humor. Obviously, the hydraulic valve is top secret in this case, because not only is the MDT covered with a steel cap, somebody put a nice steel box over the entire valve. And I don't think it was for secrecy. It's probably that in this particular lumber mill, some lumber or timber had come off the line at one point and perhaps smashed the valve. So I think that's a valve guard in this particular case, but gives you a look at what some of the typical examples are, and you can see that in many a case, these valves are running in dirty environments, dusty environments, high shock, and still a lot of amazing results can be achieved with a servo valve. All right, let's jump over to the lunchbox sessions lesson on servo valves, and let's have a look and learn a little bit about what a servo valve actually is and what's unique about it. And maybe what's mostly unique about a servo valve is how it gets used more than its design, although there are certainly some very tight design features associated with every servo valve as well. And let's just stop a minute to have a look and see who's all joined us. Certainly the list has gotten longer since we started, so welcome Egypt, United Kingdom, New Zealand, that's great. Folks in our session today from Quebec here in Canada, way down east. From Jordan, folks from Fenton, Michigan. Thanks for joining us from New Hampshire, Philippines, that's great. Romania, welcome. India, we mentioned you earlier, terrific. United Arab Emirates in the Middle East, Saudi Arabia, Mexico, Holland, Russia, Hungary, fantastic. Welcome, and hope you find something useful in our servo hydraulic session today. So in lunchbox sessions, we're looking at how it works. Here is a very typical and simplified hydraulic servo loop, and it gives us a bit of an overall picture and reminds us that there are not just one signal involved in getting that valve to become active and move our cylinder into position. There's a second very important signal. So the command signal is where it starts. Somehow we have a controller that lets the solenoid inside that servo valve know that it's time to go to work and get that cylinder moving, but it's not so much about telling the valve to open, it's that we actually desire that cylinder to move to a specific position. This is the ultimate in positioning control that we're into here. So once that cylinder gets moving, we have a feedback signal. That's what's coming out of that magnetic displacement transducer that's mounted in the back of the cylinder. That's our feedback signal that's being processed also by our controller or amplifier. And we're using that information to decide whether or not there's still a difference between what we commanded as a position and what our position actually is. And that amplifier there with that large open triangle has to either have the tuning or the programming inside it to know to close the difference. That difference is often referred to as error. Error when the cylinder is not yet in the position we have asked it for. There is an error there, and that error has to be measured, and we use that to decide how much drive signal and for how long to keep that drive signal going to the actual solenoid. Because in the end here, this final line from the controller amplifier to the solenoid, that is an electrical drive signal. In the end, that's what it turns into. But how much current and for how long does it persist? So that magnetic displacement transducer that's threaded into the back of the cylinder has a long rod or waveguide, and that actually fits into an opening in the back of the cylinder rod that's been gun drilled to a larger diameter so that that waveguide fits in there very easily, that rod, and then riding on the back of the piston, and we'll have a look at these pieces shortly here on the table, is a magnet. A donut-shaped magnet, a toroid magnet, has been screwed to the back of the piston, and that magnet is helping that transducer sense exactly what its position is at any point in time. So that's the feedback loop that is absolutely critical to what's happening here. And that should really be a critical part of that definition if we're out looking for what is a servo, or if we're looking up what is a servo mechanism. That feedback and measurement of that is a very important aspect. All right, so two signals, we learned about that. If we were to crack open the servo valve, and we will here on the desktop in just a moment, we'll find out that we've got a valve spool in there, like many a directional valve, but that valve spool may not be covering up the port that it resides near at all. It may be at zero clearance in the servo valve world. It may actually even be slightly underlapped. If a servo valve spool has lands on it that are overlapped, it will be by the very tiniest amount. A zero lapped or an underlapped critical type of valve spool is very common, meaning that as that valve moves in one direction or another, it is going to immediately produce flow either to your A work port for extending the cylinder or to your B work port for retracting. And so it is very difficult for that valve by itself to find its home and center position. It usually does take the feedback instrument to help that valve achieve its center. If you've seen this type of diagram before, for spool displacement versus flow here, what we're basically graphing is a valve that can displace to push oil out of the B work port. So as we move to the left, that's our valve spool moving from the home or closed center to displace the spool out on the B work port and then produce flow on that B work port. Or perhaps we displace the spool the other way and produce flow on the A work port. And what you're seeing here is that our graph passes right through the center, meaning that the moment that valve is done displacing in one direction, maybe it's coming back home from the left, and we hit the zero flow mark, well, the moment that valve spool moves any further to the right, we've now begun displacing flow out of the opposite work port. Whereas in some proportional valves, you might find that there is just a little flat spot, that our line might track a little bit above this green line on a diagonal, hit a little flat spot here near center called deadband, and a little flat spot as we cross over center, and then start to take off and produce flow. And that's letting you know then that you've got a valve that has overlap. Well, with a lot of servo valves, it's zero lapped and underlapped, and so our spool displacement versus flow graph passes right through the center. And of course, the precision manufacturing of a servo valve is a critical factor, and any kind of grit, solid pieces from metals, from silica, from carbon inside the hydraulic fluid, any hard bits or pieces could have a mechanical erosion effect on critical notches in that valve. And so for that reason, you A, want to keep your hydraulic fluid really clean, and B, you want to make these parts on the inside highly accurate and make them out of fairly hard machining steel. All right, here we see an example of the spool, a hardened spool inside a hardened steel sleeve, and we're hoping that, that these pieces are not likely to wear even if there is a little bit of solid contaminant in the fluid. We'll have a look at those exact pieces here on the tabletop in just a moment. You'll see a diamond-shaped metering notch. If you've taken a spool out of a proportional valve, oftentimes the metering notches, the V-shaped or U-shaped metering notches, are cut into the spool ends. Sometimes in the servo world, the opposite is true. The metering notches are in the spool sleeve. Can you accurately meter fluid without any metering notches at all and just use the cylindrical circular area of the work ports? Yes, but then you have to have extremely fine control over that spool movement. If you've ever worked with a very basic directional valve, this is not a proportional valve, and if you work with this type of valve and you pull that handle very, very gently, you may find just a small space where it's proportional for a moment, but it's very hard to figure out how little movement of that valve lever produces a variable amount of flow. So very tough. Need to have a very accurate servo driving mechanism to achieve that. Scrolling down a little bit. Yeah, you can set up servo loops to control position. That's all we're going to do here today is position servos. But there are also speed servo loops. And force servo is another application where you use pressure to control the amount of force that a ram or a cylinder might exert. Thinking of calendar rolls and nip rolls in a paper machine is a very typical application to see servo valves hard at work, and yet they're really not about motion. Very little motion taking place, just enough to either set the nip between rolls or to produce a crown shape on a paper machine roll. And those rams are actually then inside a paper machine roll, and very careful pressure servo controlling is being done. Here's an example of speed control where our motor becomes active and produces a speed. And then obviously our transducer in this case is not a displacement transducer. We need some kind of a speed sensor measuring the RPMs of that hydraulic motor and then using that as the feedback signal instead of cylinder position. What about different types of servos? Well, we spoke a little bit about that direct drive type of servo, and we've got an example here. Here's a Bosch Rexroth valve where the electronics are on board in this larger steel cap, and the spool valve is here in the blue section, and everything that's happening over here is the electrical drive and solenoid and feedback transducer, and it's driving that spool directly. That's a direct drive type of valve. So that's a one-stage valve. Here's a little bit of a see-through imagery of what might be taking place, where you see the solenoid and some kind of push linkage directly acting on the spool. So instead of using pilot pressure, it's just electrical actuation directly via linkage to the spool. It's one stage. Another style of one-stage valve is the rotary direct drive. And you can see it moving there on the inside. Does that motor make full revolutions? It does not. It makes only a fraction of a revolution, a very small amount. And you see a small eccentric on that shaft that fits into a little pocket in the spool and moves it back and forth very, very small amounts. We're showing probably the entire movement of the spool, but the accurate controlling of flow would take place with even smaller motions than what you see there. What about a two-stage valve? Well, these have been very popular for a long time. And if we have a look at a two-stage valve, one of the typical scenarios is what you see here, a pilot stage valve with what's called a torque motor on the upper half. We'll have a look at that. We're going to look at the flapper and nozzle style servo valve. And then we have an output stage spool that is moved back and forth by pilot pressure from one side or the other, and that output stage spool drives your hydraulic cylinder or hydraulic motor. What's in that torque motor? You've got some permanent magnets we've removed from view there directly in front. You've got your coils producing electromagnetism. You've got a T-shaped armature, which will be easier to understand in a moment when we take it apart. And, oh, yes, a couple of very tender little springs that help that armature return to center. Oh, very, very sensitive springs indeed. So remember those when we get around to looking at mechanical nulling of this type of a valve. So there it is. There's a little bit more of the torque motor stripped out. And what we're showing you there is that as the coil is energized with current in one direction, it will tip that armature and not very far. Those gaps, when they're all even, you'll see here in a moment, are very small. And that torque motor does not tip very far to one side or the other, depending on the direction of current. And that deflection becomes so important in moving the flapper towards one of two pilot nozzles that are continuously just feeding oil from the pump supply side of the valve through small orifices and then back into that center gallery on the main spool below, which is the return to tank port. And that nozzle is moved against one side or the other and creates an imbalance in the pilot pressure. Yes, you're seeing it here in this next scenario where if our flapper has moved against the right pilot nozzle, it causes a build in pressure on the right-hand side of the valve spool, and the valve spool moves to the left, and now here below you see we have begun to produce flow out of one of our work ports. Yeah, on this style of valve, the P port is usually on each end, on both ends of the spool, or just inside the pilot piston of each end of the spool. Return to tank, often in the middle in this design. And what about that linkage? So there's a little feedback wire that's actually connected to the spool. And isn't that an interesting scenario? That while the spool is shifting, the linkage is actually moving that armature back towards its original position. And so here you have a bit of a closed loop servo effect almost in its own right inside the valve. And that continues until the armature, along with the flapper, are recentered and no longer restricting flow. But keep in mind that your electromagnet is still active. If you haven't canceled your signal, the electromagnet is still trying to pull the armature away from center. So let's see all of that fun here in action in 3 dimensions. We'll just get that video to run. And I think what you'll see here is all of that action. There's our pressure coming up on the right side. The spool moves left and pulls the armature away from the nozzle on the right. And so that is the automation of the appropriate amount of pilot motion for inside the valve itself. Okay, more on that here in a minute when we get to some other 3-dimensional artwork that we have. You saw one example in my slides of a 3-stage, or maybe 2 examples I had. And yeah, it's basically a 2-stage servo valve sitting atop a fairly large spool that's required perhaps to drive some very high flow rates to a large cylinder that's still expected to move very quickly. So it's basically a 2-stage servo valve sitting on top of a large spool proportional, a large spool valve, and all of the control electronics will usually be down there on that bottom 3rd stage, and displacement transducer as well to track the positioning of that main 3rd stage for the high flows. Yeah, here's a little bit of an example. Let's try this one out for controlling speed. There we go. Perhaps it's a very, very large hydraulic motor. So you'll see there's a number of pieces in action for such a large valve. It's all about the high flow rates in that example. All right, let's go back to, let's take a moment now, and maybe this is a good time to answer some chat questions. And I see also we've had folks joining us from Maryland in the United States. Great, welcome. and the Bayou in Acadiana, and we've got folks who have joined us from Turkey, so welcome. All right. Karis is asking a question. Does anyone know the machining tolerances of a servo spool? Yeah, Karis, I'm not sure I have the right instruments around here to make those measurements as accurately, but I hear that they can be as little as 1 and 2 microns, the clearance between the spool and the sleeve, or the spool and the valve bore. And so I think that demands the highest tolerance in machining and then final inspection. And again, makes the point about why we really can't have any amount of noticeable solids in that hydraulic fluid. Trouble is sure to come. But I can't say that I've got the tools to accurately make those kind of measurements. But what my understanding is as close as 1 and 2 microns. We take that meter stick and divide it up into 1,000,000 little increments. We take 1 or 2 of those, and that's it. There's our clearance. Very tight clearances indeed. Also a question coming in from Ian. Welcome again, Ian. His question is, what's the best way to explain the difference between a servo and proportional? Yeah, maybe this is a good time to address that one, because we're going to jump onto the tabletop here and look at some parts in a moment. And really, if you go back through the discussions on various hydraulic forums and expert journals over the past few decades, it really has settled on the discussion that any valve that can be modulated electrically and produce a variable amount of flow that provides the adequate amount of response needed to, in a timely and accurate fashion, move your servo cylinder into the position that you need, is a valve that can be called a servo valve. If it helps you get your servo cylinder or your servo mechanism built and it has the right response, that valve can be thought of as a servo valve. So that is why the styles, I guess, of construction now vary as much as they do. I have seen some discussions from the experts and professors at Milwaukee School of Engineering that I think about 15 years ago were having, and basically settled on a definition for their purposes that a servo valve was any valve that had less than 3% of overlap, and I think that includes all the valves that then move into the zero lap and underlapped spools as well. I think the ISO standards have some slightly different designations where they speak about the testing pressure that servo valves are flow rated at, and that doesn't that doesn't give you quite the same distinction that many are looking for. So again, it seems that the modern day discussions center around, is the valve responsive enough to deliver the necessary accurate servo action? Then it's a servo valve. What is a Moog valve? Someone is asking. Moog is a manufacturer of valves. They've been at the game for a very long time, perhaps with only 2 or 3 other original manufacturers who are very heavily into the servo valve game at an early stage. So Moog is a brand name, and they are still in the business of producing servo valves, both of the 2-stage design, multi-stage design, and direct drive spool-driven servo valves as well. All right, well, then we've answered a few chat questions here, and that makes it a great time for us to have a look at some of the bits and pieces that I've got with me here on the table. So what I've cut in half here is I just cut right through one of these Moog valves. So if you were interested in the Moog valve, we just simply sliced right through, and there's the main lower output stage valve body. And maybe, a part that I should have taken out, maybe you'll be able to see inside, is running from one end to the other with a couple of little stop pieces. If you look down inside there, you'll see it. There's a filter in there. It's a mesh filter that's just there to try and trap little particles that may have made it into the valve before it passes up to the torque motor pilot stage on top. So that's where, if you say that doesn't look like a very accurate valve bore. Well, that's not the finished valve bore. There was a cylindrical spool sleeve in there. Looks like we managed to cut that one in half as well. Maybe it's the bigger half because we weren't right in the center. Yeah, there we go. I think I've got the right half of it now. And so that spool sleeve was trapped in there on both ends with the pilot caps. You could see some gasketing there that controls where the pilot passages are and how that gets to push on each end of the spool. Do I have the right spool? Yes, I do. So that sat in there like that, and pilot pressure would build under one end or the other to move that spool back and forth. And there's that little hole in the spool there for the feedback wire. Here, I'll just stack up enough pieces on top until they just start to fall out all over the table on me, which will typically happen. And let's just see what fun we can have. So there's our torque motor pilot stage sitting on top, and the little feedback wire with a little ball sphere on the end fitting into a little drilling in the spool. And so there's kind of our complete structure, if you will, more or less stripped right down. And if I take that spool sleeve back out again, and we just have a look from the opposite side, we see those triangular metering notches for this design. And there were 4 all the way around, but we've cut that spool sleeve in half. And maybe if I just try to get it in the center here, you might say to yourself, hey, is that valve spool now closed? Well, I did measure that with my digital caliper and found that the measurement there is just about identical, perhaps not exactly the right instrument to give an accurate measurement, but you can see that I don't have to move very far from the center position, and I've uncovered the work port on one side or the other. The work ports are the diamond-shaped ports. So that's the action that we're talking about when you imagine what's happening with the output stage spool. And on these Moog valves, the return to tank was in the center, and the P-port, the original pump supply pressure for moving the actuator, is here in between. That gives you a little bit of look at the output stage of the valve. And then here is that pilot stage torque motor. Yeah, those couple of very critical soft springs that are a part of recentering that T-shaped armature back into the center. They've gone missing there, but you'll see them in our three-dimensional views here in a moment, because these gaps here, when the valve is neutral, should be exactly even, these 4 gaps, 2 on one side, 2 on the other, and that should then be holding the flexure tube. That's a word for you, but that's part of the Moog literature for this type of valve. That drops out of the bottom of that T-shaped armature is there, which makes up the flapper that moves against one nozzle or the other inside this bronzed block. And pilot pressure is shipped up into the nozzle block through one port or the other from pump supply from the lower half of the valve. And so there's that action. It's a very small amount of deflection. It's basically, if you've ever heard somebody say, isn't this style of servo valve basically a Swiss watch on top of a proportional spool? Yes, I think that's an apt way to describe it. Absolutely correct. Okay, so that's a spool style two-stage valve. Let's look at a one-stage valve, and we've got a rotary direct drive style here from Woodward. Some of you may have known this model in the past as an HR Textron, belongs to the Woodward name now. And so I'm looking at the bottom of the DO3 port structure there. Our O-rings went missing. And there are no metering notches here. It's all just direct circular cylindrical openings. But the control that the rotary torque motor or the rotary motor has over the movement of the spool is very precise. Insanely strong magnetism in the middle of the drive works on the motor part of this valve, and so this is a valve spool that can be moved back and forth very precise amounts to let flow out of either your A or B work port and drive your hydraulic cylinder. Here, let's find that center shaft that has the magnets in it. There it is. There's that eccentric, and again, that valve is moving that spool just a portion of a rotation. So while it is a rotary motor, it's not a motor that makes any complete revolutions, and it indeed makes some very small partial revolutions to produce the desired flow rate. Very strong magnets in there, as you can see, and some very precise windings around the outside. Everything's starting to stick together because, hey, it's magnetism, and that's how that works. All right, so you've had a little bit of a look there, and while we were looking at pieces just lying about loose on the table here, we might as well have a look at a pretty typical magnetic displacement transducer. These come with electrical output in a variety of style. Could be analog voltage out, it could be 4 to 20 milliamps current out. Other styles that are very popular with servo cylinder controllers are a pulsed style of output called start-stop, or PWM, pulse width modulation. And there's that magnet. That magnet is mounted directly on the piston, on the back of the piston inside. And so as the cylinder extends and retracts, the distance from the sensing head to the magnet is measured. It's measured by sending out a pulse, a burst, down a wire inside the center of this tube, the waveguide, and that pulse travels, if I remember right, every inch of travel takes about 9 microseconds, but slight tuning differences for each unit. And when it hits the magnet, it bounces off of an intersecting magnetic field produced by the permanent magnet. That's why this style is often referred to as magnetostrictive. It's a constriction of magnetic fields that happen right where that magnet is, and the pulse bounces back to the head, and the amount of time it takes to travel to the magnet and back and be received by a little strain gauge inside, that time is measured, and that measurement is then an interpretation of the distance, the physical distance from the sensing head to the magnet, and that can be calibrated and resolve quite easily. You can resolve to 1/1000th of an inch, or even greater detail than that, depending on how long and short the sensor is. It easily resolves to 1,000th of an inch. So that's your typical. And if you may say, hey, is it only an MDT if I've seen this type of red box sticking out the back of a hydraulic cylinder? No, you can get that same type of structure set up so that all of the electronics are actually hidden inside the cylinder, gone internally and inside the cap end of the cylinder, hidden from view, and perhaps sticking out the side of the cylinder is a connector like that, and then you're wondering maybe what's inside, but same technology in all likelihood. And if you know the M series of graters by Caterpillar, like a 12M, 14M, 16M, 24M, the steering on the front end of those graters now is basically a servo loop. And you might say, hey, I didn't see a valve mounted on the cylinder. Now the valve is back closer to the cab, and you might say, hey, that doesn't sound like a very stiff servo. Well, it's not necessary for the steering to snap into the kind of action that you see as the snap action motions for some factory manufacturing, and so it can still be done quite accurately. It's just not required to be as snap fast as some other factory servo applications. One last MDT that we'll have a look at is the dry style. It still has a magnet inside. It's just not meant to go inside of a hydraulic cylinder, and so that can be handy if the cylinder is too small to have a wet MDT mounted inside, or it can be used with all kinds of other mechanical mechanisms that are not hydraulic cylinders to measure position. And you might notice here that on our training units, we have both. We have both the, you'd have to look underneath here, but we've got both the wet MDT, which is using the magnet inside the cylinder, and then we've got the external dry one, and that can be a handy one for us to be able to have flexibility here and deliberately create some error as though the magnet isn't sitting nicely in place on the back of the piston. Yeah, so I hope that helps just sort of give you a bit of a direct view of the parts and pieces in there. And maybe just while we're at it, a few last bits and pieces about the accuracy and response of a servo valve, because if you look at these pieces and say, hey, I'm pretty handy with the lathe, I could make that. Yeah, probably most of us could hammer together enough pieces to get the basic functionality to occur, but what about the accuracy and the speed of response? And so a common term to start discussing in the area of servo valve is the frequency response of the valve. And you'd say, what is that all about? Well, basically what we're looking at when you examine the frequency response of the valve is if we signal the valve's solenoid, if we tell it to jump into action, how long is the delay until that valve spool travels and starts producing the amount of flow that matches with the signal that we sent to the valve? There may be a delay. There's a mass here, there's inertia, there might be some slightly compressible oil on one side or the other end of the spool, and so there may be some time before that valve spool arrives in place. And if it lags behind the signal we sent to the valve, and then we're looking at an issue where the valve is not necessarily staying in phase. The output of the valve is not staying in phase with the input command. And also the amplitude, meaning how much flow came out versus the signal that we sent. And so what happens is in frequency response testing, they send a sine wave, and this is done, of course, by the manufacturers, who then publish the capabilities of the valve after they've designed it and achieved the best results they can with a particular design. But they'll let you know how many back and forth sine wave drive signals can you send to this valve per second. That's your frequency. How many can you full oscillations back and forth can you send and expect this spool to keep up and be in the position desired and produce the amount of flow desired matching with the sine wave input signal? And for a lot of valves, it's easily up to 10 hertz, where for 10 hertz, you will easily have all the same matching responses, and then perhaps by the time you're at 15, the valve is lagging. Perhaps by the time you're at 20 or 50 hertz, maybe the spool is lagging behind by a quarter of the entire spool's drive travel, and that may be very objectionable. You may have a valve whose response now is not adequate for the reaction timings that are required. So that's the frequency response issue that goes with. Oh, sent my magnet flying. That's the frequency response issue that goes with very carefully designed, tested, and refined and carefully manufactured servo valves. You see those graphs on the specification data, application data for different models of valves that you might look at. Oh, and by the way, I didn't mention it earlier. On our description for the YouTube below, there should be some data sheets that you could download, and you'll be able to see some of those graphs and some of the specifications for the exact products that we're playing with here on the tabletop and running live on the training panels today. All right, let's see where we're at here in my list. I'm just going to catch up with my list of things, make sure I'm still following my intended order. You bet. All right, we've had someone join us from Iran in the last few minutes. Welcome. Why do so many proportional valves? Kalpesh asks, why do so many proportional valves have a lower hysteresis than servo valves? I'm not sure. I'd be interested to seeing which models you're referring to, Kalpesh. In my experience, at least the servos and proportionals that I know, I believe I've found it to be the other way more often than not, but I could be mistaken, so feel free to email me some data sheets, Kalpesh, and I'd love to get into that with you. I'd love to have a look and compare some. info@lunchboxsessions.com if you'd like me to have a look at a particular data sheet for a proportional valve or a servo valve that you've got some experience with. Thanks for that question, though. Carl Carey, he's asking, that wire that's connected to the spool is used to center the spool. Yeah, well, that's part of it, right? It's part of a larger feedback scenario that's at work in here to make sure that our spool doesn't travel too far is really what we're into, that a proportional amount of pressure change on one end of the spool or the other doesn't end up driving us hard over. So if we send pilot pressure to this side here where my thumb is, and that's the higher pressure because our nozzle was against, or sorry, our flapper was against the nozzle here on that side, and we produce that higher pressure stands the risk, whatever pressure value that is, of driving our spool hard over all the way. And so if it's a slightly higher pressure than on the other side, we may only want the spool to travel part way. So as it begins to travel, that feedback wire pulls it away from the nozzle to help us achieve the desired amount of flow opening on that valve. So there's almost a little bit of a closed loop of control just inside the valve itself. Rather ingenious little mechanism, whoever first worked that out. Yeah, more on the lesson on that in lunchbox sessions. All right, welcome participants from Ghana. That's great. I'm not sure we've had participants from Ghana before. All right, we are now going to do some live work on the hydraulics once again, and I promised you that we would take that screw out of the valve. Actually, on a lot of the Moog valves that I've got here, instead of having to take that screw out that's above the connector, sometimes the later models just plain old had an adapter hex key piece that would connect to the nulling feature, and we'd come out the back. Oh, I know what I skipped over. We were going to first have a look at the three-dimensional videos that match with this. So let's do that first, and then we'll go to the live running hydraulics. So let's have a look at some 3D here. I think that'll help also clear up some functioning of these valves. So let's have a look at that two-stage. We won't play the whole video, but we'll have a look at a few of the bits and pieces here. Let's zoom on inside a two-stage flapper and nozzle style valve with that Swiss watch torque motor up on top. So there you see all the pieces flying out and orbiting. That bronze nozzle block is not two pieces. We split it in half just for clarity. Otherwise, everything else is as it should be. But we cut that nozzle block in half so that you could see inside better what the passages are like. We've got some permanent magnets involved, some steel pole pieces which help direct the magnetic field in the right place. There is that T-shaped armature and a couple of really sensitive springs up at the top there. Very sensitive. They may look like springs out of your ballpoint pen, but I don't think that's where they came from. I think they were probably more carefully made than that. There's that null adjustment screw. Those nozzles, they look like screws on one end, but they've been cross-drilled and bored down the middle halfway through to be able to direct that pilot flow. Sensitive little machined pieces there. So that gives you a little bit of an idea, and we'll just put that top section back together just so you can see that, and then we'll call that done for that video, because the bottom section is a little simpler, and I think you saw the pieces quite close up when I had it in front of the camera. But let's bring that nozzle block back together. It was not two pieces. We just did 3D to saw it, but you'll see a little soldering happening there. Some very careful soldering to get that flexure tube part of the armature there that allows it to pivot a little bit in that flexure tube there. Somebody does some careful soldering or some process. I can't imagine what that looks like. Would love to see that in action. All right, so that takes care of a little bit of a look at that video. And mechanical null, we're going to do that here in just a second. So let's just activate another three-dimensional movie here and have a look. If your cylinder was drifting, with the cable disconnected, mind you, and the cylinder was drifting, that would let us know that something about the spring tension and the wear perhaps of that armature, that flexure tube, and maybe the valve has just plain old suffered a lot of harsh usage and abuse. But if that valve is not allowing that cylinder to be stationary when the cable is disconnected, then it's simply a matter of changing the tension ever so slightly on those very delicate springs up there at the top of the armature. So if the cylinder is creeping, in comes your hex key there. It's an 1/8" hex key for these Moog valves, and it doesn't even usually take as much of a turn as we show there, perhaps 1/8 of a turn of the key or 1/4 of a turn, and that motion should stop. And of course, servo valve manufacturers say if this has to happen more than once in a blue moon, probably something very bad has happened. Maybe the valve has been badly cooked or overheating or overdriven with the wrong current and has suffered some internal damage for that reason. Here, let's have a look inside that rotary direct drive valve and just see what the pieces look like as that valve is taken apart and reassembled. And nulling in this valve can be done by removing those two plates and rotating, but the valve manufacturer lets us know that if that's needed, something very bad has happened. If the valve is out of null, it should really be sent back to the factory or a factory rep to have that valve properly recalibrated. Well, there you see some of the pieces involved with that style of rotary direct drive valve. Let's put it all back together here. And if we'd like to see that one in action, here, let's have a look at a little bit of the three-dimensional action of what that valve is up to. Very small motions on the inside there. So we'll just dissolve in there. This is brand new 3D that was just finished here. And so you're getting the first look at it. There you go. Just, you know, we're showing the full motion range really, but much smaller amounts of rotation yet that are possible for sending out just the right amount of flow as you might start to accelerate a hydraulic cylinder or decelerate it as it achieves the target position. All right. Now let's go ahead and do some running of live hydraulics, and we'll demonstrate nulling of that two-stage nozzle and flapper style Moog servo valve. So I'm just going to turn my hydraulic pump back on here. Oh, I think before I do that, I'm just going to make sure that I'm in the right position there and power is on. Yeah, I'm just going to uncable that valve. I'll remove the cable from the Moog type valve here. Lots of threads on that amphenol connector. All right, power back on. So, yeah, our valve is nulled because our cylinder is not adrift. If you're watching the cylinder and the driving mouse, I'll move over to this side. And I've taken that cap out already in advance. I'll get my 1/8 inch hex key in there. And I'll see if I can move it out of null then so we can see the mass and the cylinder moving. So there you go. I did about a half turn counterclockwise. My cylinder's on the move. It shouldn't be. There's no drive signal being sent. The cable is off, so my cylinder is out of null. And in order to null it, I'm going to have to now throw it out of null the other way and get it to start. So this is mechanical null. And as you now know, we're not moving the spool. We're merely changing the tension on those two springs that you saw inside, one on either side of the armature at the top, and we're just affecting the tension of the spring on one side, and I'm just inching my 1/8 inch Allen key back to where I was in little tiny portions of a 1/16 of a turn, little increments, and I'm watching to see if my cylinder stops moving. And you may need to get a dial indicator or something on there once you get really close, because it can be very small motions taking place and you want to try and get it as accurate as possible. For now, I'll say that that's it, and if all went well, I would put that screw back in. There's that screw that came out of there. I'll just leave it out for now so I don't have to do any upside down screwdriver acrobatics, and we'll cable that valve back up. Off to the races we go. So that's the nulling of a valve that allows for mechanical nulling from the outside, because now once you're back in cabled up, if it's still drifting, if you've mechanically nulled and it's still drifting, well, now that's a drive signal issue. You've got to look at what your drive electronics are. We've got a manual analog driving amplifier for the valve on this side. We can flip a switch and change over to a Delta RMC 75 and control it that way instead. That's on the other side of the stand. But this manual electronics is basically set up to allow us to command positions between the bottom of our 12-inch stroke when our potentiometer is pointed to 3 o'clock, and if I point it to 9 o'clock, that's the position called retracted, and that doesn't look very servo-like because it basically looks like I'm just opening up a valve and asking for full extend, full retract. And so maybe that's not as much fun as the positioning we could get into, as if, say, we move that potentiometer to about 1030. Okay, so if 12 o'clock is 6 inches of stroke, then about 1030 on our potentiometer should be about 3 inches of extension on that rod, and that's what it is. So this is not so much a decision for how much valve opening I want. That's not that at all. This is me calling for a position. That's what's going on. But it's very much a manual, analog type of electronics at work here. But lots of good, useful things can be learned from it by working with it in that way. I'm going to leave that pump running now, and we're going to jump over to another type of controller, an analog type of controller that one of our clients likes to use. And again, there's no programming in here. Have you heard about PI and D? We'll mention those just briefly here in a moment, but PI and D, proportional, integral, derivative, these are terms that apply to a type of calculation and corrective control that is sent to the solenoid and drives that valve to try and get us to move at the right speed, close the gap between what we've asked for as a position and what we're currently achieving, but not overshoot, hopefully, and not have to bounce back and forth to find that final position. But this one has to be tuned with an oscilloscope and screwdrivers. It's a little trickier, but let's run it over here on the cylinder that we have. I'm just going to make sure I've got everything set up right. Yeah, looks good. So again, we have a potentiometer, and this, like the other system, is literally just asking for a position. This is not like telling a proportional valve to open up a certain amount and keep on flowing. No, this is us asking for a particular position between 0 and 6 inches. That's what's happening with this. So that's a command requiring a position. Oh, now if you're watching the cylinder, and maybe I'll bring it back down to just the top of the aluminum panel, it might be a little easier for the viewers to detect. But if you're watching just up at the top here of the cylinder, can you see that it's not settling? Notice that our cylinder is going up and down. I'd say by about 2 or 3 millimeters. I don't know, can you detect that where you are on your screen? You should see that it is not settling in. Something's not quite right. And that means we need to do a little bit more tuning. That cylinder is continuously finding the target position and is then overshooting and passing back under it. It's having a tough time settling in, and that is perhaps because our proportional gain is set a little too high. It's a screwdriver and oscilloscope tuning for this one. We're not going to jump into that procedure with what limited time we've got, but suffice it to say, in order to get the cylinder to be very responsive, but then stop and settle at our desired target position requires some fairly careful tuning. Hey, you know, this is also a good time for us to, I'll just move this up a little higher here, and we'll use the dry temposonic just to demonstrate briefly the error-correcting nature of a servo. The error-correcting nature of a servo mechanism basically says that the whole control system says, I'm trying to move the cylinder to the desired place that you want, and when I arrive, I will stop there and stay there. So by having a flexible plastic piece connected over to the dry temposonic, the dry magnetic displacement transducer, that is the one we're currently using with a manual tuned controller, we've now got the ability to basically make the magnet on the back of the piston drift away from its ideal location with the flexibility of that plastic piece. So maybe I'll just stand over on this side for a moment if I'm out of the way of my camera. And what do you think will happen as I lift up on the wrench here? What will the cylinder do if the servo mechanism control is actively monitoring the position? If I lift up, if I bend upward on this plastic piece, the cylinder will do what? Extend a little or retract a little? Well, let's see what happens. Here I go. I'm going to lift up on that dry temposonic, which drifted the magnet. And you saw the cylinder withdraw because it assumed that somehow it lost the position, that it moved ahead. the control system doesn't know exactly where that magnet is, but it assumed that the cylinder moved out of position and it retracted to try and pull it back. Now I'll go the other way. I'm going to pull down on the wrench, pulling the piston downward, or pulling the magnet downward, and the control system immediately thinks that the cylinder drifted out of position towards retract and instead extended it. So the flexible piece here lets us have a look at how hard that closed loop positioning control is trying to keep up with some disturbance. That's not normal to have this much disturbance, but maybe also speaks to why the wet MDT, the wet displacement transducer that's mounted directly into the cylinder with a magnet on the very back of the piston, is a more desirable way to keep the system stiff and accurate. Hey, thanks Trigger Tech about your thoughts on our T-slot aluminum. Yeah, we do find it a very flexible material to work with. So thanks for the compliment on how we put our systems together. All right, we're getting towards the end. I hope there's been some useful bits and pieces in there for you on how things work. I'm just going to take a moment here now to remove the cabling from the valve. This is one of those rotary direct drive valves. We happen to own the very smallest one in the series, and that keeps it lighter for our travels and what have you. And that's what's going on with that one. I'm going to take that one off, and I'm going to connect it back up to our Delta controller here, because as difficult as it is to tune a PID, just a moment here to make sure I get my connectors lined up. There we go. I think most of you realize that it would be pretty difficult to tune a PID controller with an oscilloscope and manual controls and what have you. It's much easier to do it with software. And so the example with RMC Tools here, which we'll just have a look at on the page, on the software here, I'm just going to get the right mouse. Got a couple of computers on the go. And I'm just going to find my tuning tools here for axis 0. And we'll launch a tuning wizard. And we'll make that go. And a warning that I might make some very heavy or dangerous equipment move in my plant, and be careful. And then the standard 2 moves in each direction should work. And some parameters I could change if I want to, but quite often the starter parameters are just fine. There's going to be one move where we extend the cylinder and see what that's like working against, and our cylinder is very lightly loaded, and then another move, negative, where we're going to retract the cylinder, and the MDT feedback, and the response of the system will be automatically, oh, I didn't put my, there we go, I got to put my controller back into the program mode. And so we'll move to the start position. And so the cylinder is moving right now, if you could see that in the other camera. So it moved to our starting position, which was close to retracted. And now we're going to have a short move positive. And in the background here on the screen, you can see that a plot was made. And the response of the system was carefully mapped. And now we're going to switch to our next, where we move negative. So this time it's going to extend the cylinder. And oops, I didn't move to the start yet. Let's move to the start positions. You'll see it's extending our cylinder to a place where it can easily retract a little bit. And maybe the load coming back under gravity might be quite different. Our system is very lightly loaded. There's no major mass sitting on top of it. But still, you'll see the process of it. There's a move negative. And once again, the response of the system was automatically graphed using the MDT to see how smooth that motion was. And with that all done, instead of using an oscilloscope, gains have been calculated for us. So there you see some gains. Proportional gain is about making sure that the amount of drive, the corrective drive signal sent to the solenoid is in proportion to how much error there is. So the error is the difference between the command the target. And if that error was fairly large, however large it was, the proportional gain calculation is made. Whereas the integral gain is calculated off of the persisting amount of error, because proportional never finishes. It's always proportional. It leaves you with some error. And integral says, how long does that error persist? I'll continue to give a corrective action to try and finish up closing in on the target. So that's a second calculation. And then the derivative gain, the final one, is based on how fast the change in error tends to occur. It's a bit more of a predictive type of response. And then those are just automatically applied when I say apply gains. And those values are copied into the setup for that particular axis. And now we're all set to go. Maybe I'll see if I can put it back into run mode here. And we'll have a look at the trend plot and just see the axis in action. Let's just see if I've got everything set to go. It's my axis 0 program. And let's see if I've got action here. Yep, my cylinder's back in action. And now I just have to get my plot tool to open up in the right place. And I'll just do that. And let me trend. Let me just make sure I'm trending the right axis. Yes, I am. Okay, and I'm just going to turn off the velocity graph. Velocity can be very important, of course, in a servo scenario, but I'm just going to turn off the target actual and target velocity and actual velocity, and just so we could see just a little bit more simpler plotting of what is taking place. So that red line on the software is the actual position of the MDT. And the green fuzzy line there is the output signal that's being sent to the drive solenoid inside of our servo valve. Now you might say, what about the target position? Because the target position is being called for by a little program I wrote that's asking for the servo axis to jump to a few different steps, 2 inches, 4 inches, etc. Well, where is that turquoise colored target position? Well, the axis is very well tuned, so it's hiding underneath that red line. If I turn that red line off, which was our actual plot position, now we'll see the target. That very light blue turquoise line that's running up and down the screen is the positions that our program is asking the cylinder to move to. And if you can't see any difference between that and the actual when I turn the red line back on, if no part of that turquoise line sneaks out from underneath that red line, that means we're following. We're following perfectly. And there's a lot more to this. So PID tuning is an art and a science and a lot of math involved, but at least that gives you a little bit of an idea as to how that type of thing works. Let's have a look and see if we've got any remaining questions here. Hayuza wrote in saying broken main spool spring in a pilot operated, in a proportional valve. Oh, Rexroth 4WRZ. Oh yes, I know that one. Very large, heavy proportional valve. Could it be replaced by a third-party spring? No, I don't think so. That's a very sensitive spring, and I think in order to get the response you need from that single spring, which does a great job of giving you the same kind of response on each side, you'd probably want to go with a factory or original. The force behind that spring will be quite important. Yeah, you'll want to get the original spring for a sensitive valve like that Rexroth 4WRZ. But great question. All right, so that pretty much closes off the time that we've got here today. Thanks for joining us, everyone. Lunchbox sessions and the services of CD Industrial Group are brought to you by myself, Carl, Owen, Mark, Nathan, Crystal, Robin, Chris, Ivan, Alex, and Lenore. And special mention also to Ted, Keelan, Emily, and Grant for their contributions throughout the year. Thanks also to Fluid Power World, our partner for this series of sessions. There's 2 more coming. And thanks also to our sponsors, Delta Computer Systems and servo kinetics. Our next live broadcast will be on July 14th, and it'll be all about slip-in logic cartridges. If you know those big square covers that sometimes don't look like much on a manifold, and inside is that cylindrical cartridge on a large valve manifold, that's the topic we're covering on July 14th. I hope to see you then. Thanks for joining us today and being participants in our live broadcast. This is Carl from lunchboxsessions.com, and we'll see you next time. Bye-bye. We're off the air?